Hello and welcome back to the first lecture of part 2. In this part, we're going to talk about how AI can help us. Now, at the end of the first part, we introduced some examples of the application of AI in medicine. And I'd like to pick up from there today and start off with probably one of the more obvious applications of AI in medicine, which is breast cancer, one of the more important challenges of women's health. Now, AI algorithms basically have taken the digital image of the breast and converted them into pixel level variables. And then these variables are then used in order to try and recognize patterns which are associated with tumors. Now, these variables are most often not recognizable to the human eye, and so of course, the interest is to see if there is something that can be recognized that the radiologist does not appreciate. Of course, this is a challenge because the ground truth is going to be based on what the radiologist sees, as well as follow up in terms of does the patient actually get cancer, so have a tumor which is biopsy proven. So it's that mix that's going to make building an AI solution challenging, in that you can train based on the labels from a radiologist, and therefore the best you can hope for is your algorithm is going to match that of a radiologist's ability to diagnose. If you train then on images that are associated or that are backed up by a biopsy proven cancer, then there is the chance that you can work with these pixel level variables that are just automatically obtained during your processing of the algorithm, if you wish. And then that way you're hoping that you could exceed the ability of the human eye to detect a tumor or lesion. So when you have these pixel level variables, and there are many, many, many millions of these, the goal is to identify new imaging features that would be associated with your hard outcome, which is breast cancer, which would be biopsy proven breast cancer. And this association with your outcome data is what you're going to use to train your algorithm. So ultimately, what we're aiming for is an AI algorithm that can combine these pixel level variables and associations with our clinical outcome, which in this case is breast cancer, and then to also include any history or patient risk factors that would also help in diagnosing cancer, and to ultimately end up with a predictive algorithm that will be equal or better to what is currently being done by humans. So many of you are right now either thinking one of two things. One is, yeah, obviously the computer is going to be successful in, out competing the human. Or you're thinking, that's never going to happen just because I know or I appreciate the complexity in what needs to be done to make the diagnosis of breast cancer. I think it's going to be a little bit of both. I think the challenge, of course, of doing or matching, the radiologist and the clinician to make the diagnosis is going to be difficult in some aspects, and it's going to be easy in others. So pattern recognition is done very well by AI algorithms. However, the complexity of appreciating whether or not it is a cancer or not, based on a multitude of factors, so not just imaging, is where it gets challenging. And let me just introduce to you, a concept that I think I've already mentioned in the first part, and that is that AI and machine learning is not magic. So meaning there's no hocus pocus. It's not like you can conjure up a diagnosis out of thin air. You can't. AI and machine learning are just very good at computing, large, complex data sets. So the answer actually has to be in the data. If it is not there, it doesn't really matter how much you try, you won't get what you're looking for. And I think many people don't appreciate that because of the hype that is out there now that's just saying that, machine learning and AI is going to solve everything. It can't if the answer is not there. So those of you clinicians and radiologists that work in breast cancer, you can appreciate that when you're making the diagnosis, sometimes you'll look at the data, you'll look at the imaging, you'll see the presentation, and it won't be obvious. I mean, it's very possible that, the answer is actually not in front of you. And that needs to be taken into consideration when you're building these algorithms, that, the answer, the probability of finding or determining the diagnosis is going to increase over time when you collect more and more data. And I think that's something that also needs to be taken into consideration, is longitudinal data, which currently is only just starting, to become, apparent in AI machine learning modeling, because it's quite complex. The dimension of time is something that is very complex. So you'd say, well, great, machine learning is going to do great on that. Yes, it will, but it will take a little time for us to figure out how to actually do that in an efficient manner. All right, so where are we at with this breast cancer detection tool? A recent publication in The Lancet comments on a study from South Korea that basically has an AI algorithm for breast cancer detection, and they tested it on 3 large data sets. And essentially what it came out to was about a 91% sensitivity, which is higher than what radiologists, for instance, will detect, and a specificity of 86%, which actually is lower than what the typical radiologist will detect. And so, though this is great, in terms of a higher sensitivity, that's fantastic. The lower specificity implies that you're going to have more false positives, and that's not really acceptable. And the reason for that is you're screening, so that means you're applying this test very frequently, and so what's going to happen is you're going to have many women that are going to be told that they have to come back for another test because there is the possibility that they were positive for their first test, and this can be very distressing, and it can lead to worst case scenario, it could actually lead all the way down the line to surgery, and then finding out that it wasn't necessary. That's an extreme, of course, but that's what could happen. And so whenever you have a screening tool, you really do want to maximize your specificity. I mean, ideally, of course, you'd want a specificity and sensitivity of 100%. Sure, fantastic. But you definitely don't want to have a low specificity because you are screening many, 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 many people. And so here's one of the first limitations, that before we apply this algorithm out in the real world, we need to make sure that the tool is calibrated, if you wish, correctly. And this is the challenge that's currently being addressed, for those companies that are trying to develop, breast screening algorithms, as well as, regulatory bodies that are deciding, how can they, or when would they allow this software to be introduced to the clinical setting. And so that's something that you need to think about as well when you're working with these algorithms. You have to think of the impact of how this algorithm is actually going to be used, because you think, when you read a paper as a radiologist and and they describe a new way to appreciate your work, basically. So meaning that they'll tell you, well, when you look at these images for breast cancer, you should pay particular attention to these patterns, or this in particular image feature. And then, but what that does is it informs you as a radiologist. And so you're not you're just being mindful of recent discoveries in terms of how to do your job better. In this case, you're being replaced, so the radiologist is being replaced. So we have to be very careful that what we're replacing somebody with is going to be for sure as good or better. And that's the other challenge to this, is that when we describe a sensitivity of 91% and a specificity of 86%, you can imagine it is very dependent on the test sets. It's dependent on who did the testing, because inevitably you can have some bias creep into that, right? And so that's another challenge, is there's always going to be people that are going to say, well, how did you test it? How did you measure accuracy? What were the conditions? Is it reproducible? All that fun stuff. And so that just adds a layer of error and confidence, if you wish, to when you're going to actually roll out your algorithm. So my advice, as always, is to consider augmented intelligence as opposed to just outright replacing somebody. It should be combined with what the current state of the art is, and then as we work with it and we confirm that it is doing what it's supposed to be doing, then we can slowly phase out our part of the equation, so then leaving clinicians and radiologists the time to do something else that's more important or more useful or less tedious for them. So that's a perfect segue into a study from 2016 that found that physicians spent about a little over a quarter of their time of the day with their patients, and spent about half of their time on electronic health records and desk work or office work. Furthermore, when in the examination room with patients, physicians are spending about half their time on the computer, basically, entering data or looking stuff up. So this is a big challenge, right? And that's because it's very time consuming currently for physicians to deal with data, right? Especially big data, of course, but it requires tools, sophisticated tools, and it requires the knowledge to operate those tools, and it requires the time. And so one of the factors that's leading to burnout among physicians is the growing amount of administrative requirements or tasks that are linked to the clinical data that they're responsible for. So this is a sweet spot for artificial intelligence, in that if we can assist the medical professionals to do their job and minimize this administrative duty requirement, then in the end, that will be a good thing. Okay, let's describe how AI can help us. In my opinion, there are 5 reasons. The first, decision making; the second, efficiency; the third, accuracy; the fourth, precision; and the last one are addressing user needs. Okay, let's start off with decision making. So artificial intelligence, as you can guess, can often offer a more definitive answer, and also a more consistent answer. Now, physicians often must find information from unstructured medical literature to support care decisions, and this is very time consuming, and you can imagine, because I'm sure you live it, that trying to keep up with literature is extremely difficult. And it's been shown, there's been studies done, where, the ability for you to read, the 15 to 20 papers a day that you would need to do to keep up to date is just not feasible. And so that was, one of the main reasons for systematic reviews, which is the top of the evidence pyramid, which allows you, and is also considered what's called data synthesis. And that's where, you can read the single systematic review instead of reading the 40, 50 papers that are in there, the studies that show, what you're interested in. Now, AI can assist physicians by, implementing these complex algorithms that are going to take into account possibly hundreds of biomarkers, imaging results from many, many, many patients, and also include aggregated, research, so, published research, and even possibly, physician notes, right, from the electronic medical record. And so that's the power for this complex processing that AI offers. That there's no way that physicians, even if they teamed up and split up the work, could do that amount of work in the same time that an AI machine learning solution would offer you. So radiologists are not the only health professionals that are feeling a little threatened by AI and machine learning. The discipline of dermatology is also feeling the heat. And the reason for this is because there is also a larger component of imaging. And in their case, it's even a little more basic because it can actually be performed by a digital camera. And it has been shown that AI algorithms can outperform dermatologists to detect skin lesions. And I'm sure you've seen and heard of it, that you have this, mole identifier, that you can just download on your phone. Now, the other interesting, aspect that we need to keep in mind is that AI systems can learn from successive cases, right? And be exposed to many, many cases in very little time compared to a dermatologist. So this leads to the concept of the collective mind. And so you have this tool in your hand, literally, if you're using your phone, that can provide you with experience and insight that has been collected over many, many, many years of experience of many, many, many dermatologists. And you don't need to jam that all into your training in order to perform the task of identification. So in this case, though, you're still in control as a dermatologist, but you're using a tool that enables you to do your job quicker and hopefully make your decision in a more timely manner. And that's the the process, decision-making process that is aided by artificial intelligence. Efficiency, of course, is an important characteristic of AI/ML solutions. As we discussed in the first part, it is due to the immense compute capacity that is now available to these algorithms due to technological advances. Now, of course, efficiency is great for automating, boring, tedious, arduous tasks, and inevitably, computers can outperform many human tasks. When you want to think of, applying artificial intelligence, of course, you're thinking pattern recognition, speech recognition, which is another form of pattern recognition, image analysis, of course, and decision making, which we just discussed. But all of this, leads to an important hallmark characteristic, efficiency, which is one that is currently being leveraged a lot in the development of AI solutions. As we've already discussed in previous slides, artificial intelligence can assist physicians in analyzing big data or large amounts of data in a small amount of time in order to help improve the quality of their patient care. And it is thanks to the technological advances and the availability of high compute power and cheap storage that these systems are going to improve the efficiency of making diagnoses and deciding on the treatments. Okay, so what do I mean by efficiency? So let's go over a small example just so that you can maybe visualize, how efficiencies can be obtained through AI machine learning solutions. So let's say you have a small set of variables that determine or help you to determine a diagnosis. So these are called hand-selected variables because you're picking them. The human is picking them. And you're putting them in essentially into a model in order to predict a diagnosis. So in this case, let's say blood pressure and heart rate. But what if you could design an AI algorithm that's going to read the entire patient chart over time up to the point of hospitalization? And from that, you can as well make the diagnosis. So let's say the ability to make the diagnosis is exactly the same. So whether you do it yourself using hand-picked variables or you let the AI algorithm do it, you get the same accuracy, same sensitivity, same specificity. What's just in that alone, what's nice is the efficiency in the sense that the AI algorithm is just using the entire patient chart in order to extract the information required to make the diagnosis, as opposed to you having to use what's called structured data, meaning that you're going to have to log, enter data on all those visits into a structured database in order for you then afterwards to apply the model to that data. And so, this will avoid what I would consider specific data entry. Your patient chart always includes, the information that comes from the labs, that come from the various different departments in the hospital, your notes, that you write down. So that's called unstructured data because it's in different formats and it's not, put in a format or a structured way for a database to access. And so that in itself is a good example of efficiencies. And what you're hoping, of course, is to also include, improved accuracy. So not only is it efficient that it's going to run through all this data for you, but then it's also going to give you a better, is that the right way to term it, a more accurate diagnosis. So continuing on with our example of efficiency, we have an algorithm that can now read the entire patient chart over time up to the point of hospitalization, and it can do this for many patients in order to train the algorithm. But don't forget, it can also read images, and you can imagine depending on the resolution, the number of pixels, or if it's 3D voxels, that can be obtained from each and every image is immense. And so that's a lot of information, a lot of data in order to process to train your algorithms. So how do we do that? Well, we make use of what I'm sure you've heard of, GPU, which is the graphical processing unit. And this is as opposed to the CPU, which is the central processing unit, which is your typical computer processor. Okay, so what is a GPU? I'm not going to go into detail, but just at a high level, your central processing unit, or your CPU, is what drives your computer, and it was optimized, or it has been optimized for serial tasks, which means one after the other. And even though there are some very, very advanced, powerful CPUs that have multiple cores, and which means that it can handle many tasks and manage them, in a very efficient way. The development of the GPU, the graphical processing unit, has basically led to this ability to leverage artificial intelligence, machine learning methods because they're very, very computer intensive. And the GPU has been optimized for many, many, many parallel tasks. So all tasks running at the same time, and typically, the same tasks just done for multiple instances. And for example, and the reason it was developed was for rendering images. So it was basically developed for gaming, and for images, because it needed to provide the computer the ability to put up very complex and high resolution images onto your screen in an efficient way. And so to do that, parallel tasks make sense because you have, for each pixel on your screen, you have to send the information to that pixel, and those are all parallel tasks. So to do that in parallel will speed things up immensely. And then what happened is they figured out, well, wait a minute, that's just a mathematical task, to calculate the intensity, to put a display on your pixel. What if, we could actually use that to calculate, parallel calculations, and that would speed up the whole process, and it does, and that's how the GPU is then used. As you can see here on the right, how the acceleration is obtained is you have your application code, where throughout your code, it's your CPU that runs the code serially. However, a portion of your code, which requires a very high computer intensive math functions, is sent to the GPU for processing, and then sent back to your application, which is driven by your CPU. And so this is essentially why we have now this ability to process these vast amounts of data in very complex methods in a reasonably short amount of time. Okay, so carrying on with efficiency, let's turn to another example, the MegaDrug Search. So if you're a researcher for a given disease or illness, and you know the mode of action, let's say, and the target, but you just don't have a good way to treat it with a drug, and you're interested in finding that, there's two things you can do. One is you can create your own, a novel new molecule, or you can look at existing drugs, that have been described over time, and see if one of those could be used or modified for your disease or illness. This is something that IBM Watson decided it would, do in order to promote basically this AI solution that IBM put together that won Jeopardy and made this big splash. And so that was the first task, I think, that IBM used Watson for, and that was to search through unstructured data, so basically the literature, looking for answers for specific questions. And one of them they did was looking for medications to treat Parkinson's. And they made a bit of a splash about it a couple of years ago. And this is an example of how these AI tools can be used to increase efficiency. Because yes, sure, you can do it by hand by a team, but it would take years, as opposed to IBM Watson that took like a fraction of the time. Inevitably, this also contributes to this concept of precision medicine, where we're trying to not just apply a solution to the average patient, but to more specifically to the individual patient. And this would require a lot more research in order to appreciate how patients differ in terms of the heterogeneity of your population, and how treatments will differ in terms of the response in the patient to those treatments. So next up, inevitably, we're going to address accuracy, which of course, along with efficiency, are the two hallmarks of artificial intelligent machine learning solutions. We'll see you there.